Thank you very much. Well, let me just give a little bit of introduction. So I was asked to make this talk a little bit more like a tutorial. Yeah, maybe you might already know many of the things I will be talking about, but I've been trying to highlight some details that sometimes tend to be overlooked when we discuss about ultra-fast dynamics and especially ultra-fast spin transport. Okay, anyway, so the whole idea was to make a tutorial for, introductory tutorial. Okay, so I will just go through the stages of production of terahertz in spintronic terahertz emitters. And well, I will not really talk about spin to charge conversion, but I will try to highlight a few things that are good to keep in mind about laser excitation and what happens during the transport. And then I will show some results that we have got in how we can model the production and extraction of terahertz from the spintronic terahertz emitters. Okay, so I want to introduce something here just to be on the same, to say, in a way that we understand each other. So this can be pretty trivial and elementary. But let's just agree a little bit on how we want to describe excitations in materials. So let's suppose that we have a material. I've just drawn random bands, and let's suppose that we know that the chemical potential is there. So now you know that the bands are typically filled with a Fermi Dirac. Now, although this picture is very nice, I think it's important to have a look at the population of the electrons in a band structure in a momentum resolved way. For example, all these states here, depending on K, will be filled differently. Of course, that at equilibrium, the population will depend on energy. And then we can show the population in the three different bands by just showing the population going from 0 to 1 in explicit dependence of the momentum. So, for example, all these states might be completely empty. These ones, the ones at the gamma, might be more filled. And as we move away from gamma, the higher energy states will be less filled. Okay, this is pretty trivial. Now let me plot this in a slightly different way. Okay, doesn't work. Let me show this in a slightly different way. Let's just report these populations on top of the band structure. And then we can write like a thick line here just to represent that everything is filled. Here everything is empty. And here we have just a variable thickness just to show that these states are more filled compared to this one. So this is similar to what you would be seeing in ARPES, for example. Now, of course, we can do the same thing for phonons. Okay, so far everything is trivial. But now let's see how we can look at an excited state. And now again, I'm going through the basics. So I will start from the laser excitation. So the laser excitation is basically a process where a photon is absorbed. So there's a scattering with a photon and an electron which can be in any band at any k point, and then the final result is another electron at another band, another k point. Now, but what of all these possible scatterings, not all of them are physical, and then of course the only ones that are physical are the ones that conserve momentum. Now you know this is again pretty basics. You know that the momentum of a photon is nearly zero, so you get that the momentum of the initial photon and of the initial electron, the initial state of the electron and the final state should be the same. We need energy conservation, so and that's basically why we talk about vertical transitions. Now, of course, the transition is also modulated by the population. So for this to happen, the initial state must be populated, and the final state must have empty states. Okay, so then the population also modulates the amount of transitions that we have. And of course, then there is the scattering matrix element. Okay, so how do we show how do we picture these excitations in this way? Well, what we can see is that after a photon is absorbed, well, let's suppose that these are the allowed transitions for a given frequency of the photon, then we can visualize these excited state as some electrons that are removed from here and are put up here, and I can represent it in this way when I show the population as a k-dependent function. If we keep on pumping and absolutely nothing else happens, and we have a perfectly monochromatic laser, basically photons will be absorbed more and more. So the population here will increase, the population here will decrease, and then these eventually will switch off the transition. Okay. Now, what happens when we have a magnetic material? Well, it's basically the same thing. Is that now just we have two different band structures for the two spin channels. And of course, the two initial populations will look different, the bands will look different, and also the excitations can be different in both spin channels. Okay, so during laser excitation, there's also possibility of spin flip transitions in the presence of spin orbit, but usually this is a relatively small effect. Okay, so let's say we can neglect this. Now again, bear with me, this is supposed to be like a relatively basic introduction. So now just to, by looking at all these transitions and summing all transitions, what we basically get is the absorption of the laser. No? So if we sum on all the allowed transitions, so allowed due to the momentum and energy conservation with their own specific scattering matrix element and weighted by the populations, when we sum all these, what we are basically getting is the absorption at the given frequency at which these allowed transitions are calculated. If we scan all the frequencies, well, we basically just get the absorption spectrum. Okay, so what if we want to model how light is deposited in a spintronic terahertz emitter? Well, this is also relatively basic. So we have a multi-layer, we have the laser excitation. We know, so what I showed here is true for a uniform material with uniform laser excitation, but we need to keep into account that in general, the photon density when we pump a spintronic terahertz emitter or any multi-layer is not necessarily uniform. So we need to just calculate what is the photon density, the position-dependent photon density, and this is done so we need to keep into account for all multiple reflections, and this is textbook knowledge. So we can use techniques like transfer matrix method, and again, so if here new PhD students are interested in modeling this, you can find how to model basically the density of photons in the laser, in the pump laser using transfer matrix method. Let me just add a small, how to say, interesting thing to keep in mind. Now, usually what you have, if you're, for example, pumping, so you have your spintronic terahertz emitter and is deposited on a thick substrate, what you get because of the multiple reflections of the pumping laser, you can get echo pulses. And usually, so these are the echoes, but this is the only one that is really important and that triggers what is usually measured experimentally. So then again, if you want to use the transfer matrix method to calculate this, you need to be aware that the transfer matrix method will give you in frequency the entire, let's say, the entire deposited energy, but for all frequencies, and it includes all the echo pulses. So if you don't want to overestimate the energy that is deposited, you need to remove the echo pulses. Now, in this paper here, we have shown how you can remove, so basically modify the transfer matrix method to just include the first pulse, the first transmitted pulse, and just with an analytic expression, how you can get rid of all the echo pulses. Okay, when it comes to the optical excitation, this is just a small correction. Might or might not be that relevant, it's not that impactful in the physics. We will see that this has more serious effects on the terahertz radiation. Okay, anyway, so this is, so now what we get at the end of the laser excitation is basically like a strange, definitely non-equilibrium distribution of the electrons. Now what happens after that? Well, actually what happens even during the excitation is that the electrons will start thermalizing. Now again, just a short reminder of what thermalization means. Well, whenever you have excited states, well, let's say all electrons scatter with each other, but we know that at thermal equilibrium, all the net change in the population due to electron-electron scattering sums up to 0. But when the population is not equilibrium, then you have a net change in the electronic population. That's what drives thermalization. How would we describe this? Well, this gets much more complicated if you want to model it. I will spend a few slides on this later on. But let's just remember what is the physics that is involved. We basically need to check all possible scattering combinations that, again, conserve momentum, conserve energy. Now you see that the momentum conservation says that the initial momentum of the two electrons and of the two initial states of the electrons and the two final states must be conserved. Well, in reality, there's a possibility of umklapp, but okay, let's forget about that. So it's not particularly relevant for the physics here. You need to conserve energy, and of course, everything is weighted by the populations, and you need to know the scattering matrix elements for all these possible transitions. Now, what happens? So now there are enormously many combinations that satisfy all these constraints. And then if you were to calculate the dynamics, what you would get is something like this. So basically, that the electronic population eventually thermalizes to basically a Fermi-Dirac. Now again, just summarizing what we expect to see after the laser excitation is that the laser excites create some very non-equilibrium distribution, and we know that after a while, due to electron-electron scatterings, this non-equilibrium distribution tends to go to a Fermi-Dirac, now with a higher temperature, because of course energy must be conserved. Okay, so now what happens if you have a spin? Well, it's exactly the same thing. So you have different scattering channels, so up electron scattering with up electrons, and ending up again with, so these two channels are spin conserving, but in the presence of spin orbit coupling, you can also have spin flip scattering events. One more thing that is often I notice that is a little bit overlooked is that you can also have spin up electron scattering with spin down electrons, so this is still a spin preserving scattering. And now this is important because we will see later on that actually the laser excitation and the photon density of the pump doesn't really give, how to say, a good feeling of how the energy is distributed across the spintronic terahertz emitters, because we will see that all these electrons move across the sample, and when they scatter, they can basically deliver their energy to different carriers. And notice that, for example, majority carriers, if they move away, they can also deliver energy to minority, and vice versa. Okay, now what is the usual? Then what happens? Let's say usually. Well, I say it's not correct to say afterwards, but let's say the other important effect that happens after the laser excitation is the cooling of the electrons with phonons. So then the electronic system, so whatever we saw here is energy conserving, the energy is still conserved inside the electronic system, but of course electrons can then scatter with phonons by, for example, emitting phonons, and it means that now they are cooling down and increasing the temperature, well, increasing the energy in the phonon system. And again, you can have spin preserving scatterings, but also you can have spin flip scatterings. No? Okay, so now one thing that, now again, probably it's obvious to many here, but what I wanted to do here is to explain to let's say, less experienced scientists, is that actually all these things happen at the same time. So the thermalization of the electrons already happened during the laser excitation, and the cooling down with phonons also happens while the electron thermalization is happening. No? So, but usually this is sort of first approximation that we can do to have an intuitive understanding of what are the time scales of the excitation, thermalization, and cooling down of carriers, excited carriers. So it's usually not a very bad approximation to assume that the initial electronic thermalization can be considered to be relatively faster. And if you assume that also phonon-phonon thermalization is also fast, and the transfer of energy from electrons to phonon is a little bit slower, then we can basically assume that the cooling down of the electronic system to the phonon system can be seen as basically the interaction between two thermodynamic systems, so one the electronic system and one the phonon system. And we can assume that these two are internally at thermal equilibrium, and then they can exchange energy. This is basically okay, what is known as the two-temperature model. Now, what we expect to see. So what we expect to see, now here I'm showing time and temperature. So what we expect to see is that at the beginning, electrons will be excited. Now, if you notice here, I've put a broken line. Now, the reason is at the beginning, there's no Fermi-Dirac. So we cannot really define a temperature. We cannot really claim that the system is at that the electronic system has a specific temperature. So it will be very different from a Fermi-Dirac. But we can represent it here, how to say, intuitively thinking that what's happening is that the energy inside the electronic system is increasing. Then usually what we imagine is that in this time, then after the laser is done, the electrons will start thermalizing. They will take a little bit of time to go from a completely out of equilibrium distribution to a Fermi-Dirac distribution at a high temperature. Now notice that I'm not putting a time scale here because I will later make a point that it's not that obvious to define a time scale for thermalization. Now, of course, in the meanwhile, they are losing some energy to phonons, but then usually what is expected is that electrons eventually will look like a Fermi-Dirac, and they will start cooling down with phonons, and then on a much longer, so these are very different time scales, so they're not comparable. So on a much longer time scale, then we will have the cooling down of the sample through basically heat diffusion through the substrate to the sample holder. Now this time scale is also interesting, and so we did some work on this in this article, and here I'm saying you should see Ranjan's talk, but I think he's not, sorry, it was canceled, so Ranjan is not coming, I guess, or I don't know if one of his students. He will be replaced by one of his students? Okay, so then maybe you will see something about that in his talk. Okay, now, everything so far was pretty basic, okay? So it was just meant to how to say, it's a basic introduction. Now, let's get to something that is a little bit more interesting. What are the time scales? No? So what are the time scales? So the time scales for especially thermalization, so this is a debated topic. How long does it take for the electronic system to thermalize? And it's not a simple question because, okay, first of all, an excited state thermalizes through a number of scatterings, and all different states basically thermalize and go back to a Fermi-Dirac at different times. Okay, so if we have a strongly excited state, then it's a complex, system to describe. But let's suppose that we have a weak excitation. If we have a weak excitation, then we can assume that the time scale of thermalization at different k points depends basically on the scattering lifetimes at that very specific at those specific k points. Now here I'm showing the scattering rates, which is the inverse of the lifetime. But what we notice here is that lifetimes for different k points can be very, very, very different. So electrons, excited electrons at different k points will go back towards the Fermi-Dirac with different time scales. Okay, let's try to be a little bit more not quantitative, but let's say to get a little bit of intuition what we can expect. So whenever a state has to decay, so it can decay through electron-electron scatterings, and basically the scattering, okay, this is the scattering rates, are basically a summation of all possible scattering processes that the electrons can undergo. Now, of course, it depends on the scattering matrix element, so it depends on the populations, but if we are close to the very, very close to equilibrium, let's say we can consider them to be relatively close to Fermi-Dirac. But what really matters is this summation. So because depending on where this excited electron here, the number of allowed transitions can change enormously. So this has a huge impact on the scattering lifetimes. And then what happens, so maybe it's not that trivial to see, is that, let's say on typical materials, and if we exclude band gaps, so the higher the excited state is in energy, the much higher is the number of allowed transitions. By allowed transition, I mean all the transitions that conserve energy and momentum, and therefore much shorter is the lifetime. Okay, so here we can see this is gold, platinum. So here you can see the energy. So these are lifetimes plotted in energy. And here you can see how sharply they go up as we get closer to the Fermi energy. So now we can already see that if we have highly excited electrons, okay, then they might decay relatively fast. But as they go down closer to the Fermi level, their scattering dynamics becomes much, much slower. So it takes a much longer time to go back from an out of equilibrium state to being close to a Fermi-Dirac. And now you say, okay, we don't like it. So I told you that the thermalization depends on the energy of the electrons. Sure, that's fine. But then you might ask, okay, but what is the relevant energy? No? Well, what is the energy that we should be looking at? And it's not that simple. And I want to show you why it's not that simple. And I will show you that actually the most important energies are the ones that are relatively close to the Fermi level and that have relatively long thermalization times. Okay, but before doing that, now let's go again in how to say, tutorial mode, and let's just review some very basic concepts of transport out of equilibrium. So now you know that each state, this is trivial, has its own group velocity. So this is solid state physics 1. And so here I'm showing just calculations for different materials. What happens if we have what happens if we have a magnetic material? Well, if we have a magnetic material, then by the way, notice that here I'm showing everything independence of energy. Of course, this is a simplified view. We should always, if we want to be precise, we should look at group velocities independence of momentum and band. Okay, but this is a nice way of getting some idea of what are the typical, at least group velocities and scattering lifetimes. If we have a ferromagnetic material, then what we see, and this is kind of the basics of the superdiffusive spin transport, what we notice is that in general, majority electrons tend to have higher group velocities compared to minority electrons, and they also tend to have longer lifetimes compared to minority electrons. Okay, good. So now now again a tutorial on super diffusive spin transport. What happens? So let's suppose that we have a laser excitation. We excite a spin-up electron somewhere at a relatively high energy, and this electron will have a certain group velocity in a direction that depends on where in the Brillouin zone this electron has been excited. Okay, so in general, it can be in any direction. So this electron will have a finite group velocity, notice which is pretty high, so it can be, it's of the order of nanometers per femtoseconds or fraction of nanometer per femtosecond, and it will move in a straight line. Now, of course, that's not exactly what happens because this electron can scatter. And usually the mean free path at the beginning is relatively short because these lifetimes are relatively short. When it scatters, usually at these high energies, it scatters with other electrons, and then it will lose an important amount of its energy. It will go down, it will change its group velocity, but most importantly, it will change its own scattering lifetime. So now you notice that this part of the trajectory, the mean free path after the first scattering, can be importantly longer. And of course, it gets more and more important as we go down in energy. For the minority carriers, we have something different because now you see that the scattering lifetimes tend to be always very short. So now this motion will be much more broken. Now it turns out that when you have this can be approximated as a standard diffusive regime, but now here what we have mean free paths that are very large compared to the size of the sample. So this is basically ends up, it's called the super diffusive regime. Now, notice that what makes this transport much more efficient than this is really the fact that this is a super diffusive regime and this is closer to a standard diffusive regime. On top of the difference in the transport properties, but the type of transport makes a huge difference in the transport. Okay, and this is basically a summary, and then this is what triggers the super diffusive spin transport. Of the excited electrons, majority carriers tend to have much longer mean free paths, and then they can very effectively diffuse away from the ferromagnetic layer into the, for example, the heavy metal layer in spintronic Terahertz emitters. Minority carriers instead have a very, very broken trajectory, and they struggle much more to move away from where they were originally created. Now, of course, the real description is much more complicated because at every scattering you have more electrons that are generated and you need to keep them into account. Now, what you might ask here is, fine, this is just diffusion, no? So this is just diffusion, so we are exciting electrons and we are just describing the diffusion. But we know that for electrons at the Fermi level, we have basically two effects in transport. We have diffusion, but we also have drift. No? So what about drift? No? So what is drift? It's basically whenever you have some applied field, electric field, or some other equivalent field that can generate, basically can apply an acceleration to these carriers. Now the trajectories here are not straight lines, but they are accelerated. Now, so let's suppose that we have I don't know, spin voltage, then this will be accelerated. Now, is this relevant? Is this relevant? Well, let's look at this. So the group velocities, so the diffusion is mostly driven by the group velocity of the electrons. The group velocities of the electrons are of the order of fraction of nanometers per femtosecond. So now it means that this electron can cross basically the entire sample within few femtoseconds. What are the, so for drift, another velocity is important, which is the drift velocity. Now, what's the drift velocity? Now, probably you have studied standard transport. What's the drift velocity? Well, it depends on the mobility. And now let's try to estimate this. So the typical mobility in metals is around this order of magnitude. So now to have drift to be comparable to the effect of the super-diffusive spin transport, we basically need to have applied fields or effective fields which are of the order of fractions of volts per nanometer. And okay, so now these are definitely very high fields. Okay, now my opinion is that we can ignore drift. And well, for sure we can, the drift is obviously strongly related to the laser fluence, to the pump fluence. No? So the more you pump, the more whatever driving field you're generating. So what we can say for sure that at low pump powers, drift has a negligible effect because the transport due to the diffusion is so effective, and whatever correction we get from drift is absolutely negligible. Now, of course, if we have strong excitations, we might be able to generate these very, very high fields, and then the drift might be, how to say, competing, or let's say, or even improving the effectiveness of the diffusion. And one more comment is that this effect, of course, is linear with the power. No? So in principle, you can see effects of drift, but they should be linear with the laser power. So for example, if you check at the delay, no? Or how long it takes your spin current to reach some interface should be proportional to the laser power. This is independent of laser power, because this is just the group velocity that electrons have. Okay, and now we have a little bit of an intuitive description of the super diffusive spin transport. And I mean, of course, I never tried to describe the theory, but I just wanted to show a little bit of the basic ideas behind. So if you're interested, you can check these. These are the articles where we developed the model. Okay, so now that we have a little bit more of an understanding of the microscopic mechanism, I want to go back and answer. Okay, sorry. Let me. Now, this whole story. I mean, in principle, here I'm not saying if the electrons are strongly out of equilibrium or if they're just very hot, no, if they have a high temperature. So when we want to describe these, how should we treat the electrons? Should we expect them to be far out of equilibrium? Should the population, or we can simply just assume that the population is a high temperature Fermi-Dirac? And the answer is not easy. So that's why I'm describing. So I'm going to spend a little bit of time trying to figure out what are the most important energies that contribute to transport or to the super diffusive spin transport. Now, let's suppose that we have, now I'm going back to a simplified picture, just where I plot here the populations in the minority and the majority channel, independence of energy, okay? So I'm dropping the very precise description as a K-dependent excitation, okay? It's just for simplicity. Let's suppose that the laser excites carriers, and now notice that it creates excited electrons and excited holes in the two spin channels. Now, let's visualize them in a slightly simpler way. Let's just show the difference between the Fermi-Dirac and the excited state, okay? Because, and the reason is that we know that at equilibrium for the Fermi-Dirac, all these transport effects sum up to 0. So the only thing that matters is the difference. Oh, okay. Okay, so I'm very over time. Okay, So what happens? So let's look at how they behave. So this is more or less how the lifetimes go with energy for spin up and spin down, longer lifetimes for spin up, longer lifetimes for shorter for spin down, but also we need to follow the holes, and this is also the behavior of the velocity. Now the net spin transport is this difference between all these four excitations, spin up electrons, spin down electrons, and the holes. So when we are at excited energies, now we notice that the transport is not really that efficient because the scattering lifetimes are basically short for both spin up and spin down electrons. So anyway, these high energy excitations do not contribute much to transport. But of course, then whenever we want to calculate the spin diffusion, we need to take the difference between diffusing spin-up electrons and diffusing spin-down electrons, but also notice that we need to take the difference between spin-up electrons and spin-up holes. They transfer opposite spin, so we need to subtract these two channels. Now, usually you see that the holes are relatively slow, so to a first approximation, we can neglect holes unless they're close to the Fermi level. Now, let's see what happens if the excitations thermalize, by scatterings that get closer to the Fermi level. So now we see that the transport is much more efficient. So now we see that this is really like a super diffusive transport with long lifetimes, long mean-free path. And now we can really say that the transport is really the difference between the transport in the two spin channels, but also between the electrons and the holes. So notice that if we get too close to the Fermi energy, the behavior of electrons and holes become the same. And since in the same spin channel they carry opposite spin, they start canceling each other. So basically what we can conclude is that high energy excitations don't contribute much. Middle energy excitations contribute a lot because they have high lifetimes, but as we get too close to the Fermi level, then the effect of electrons and holes start canceling each other. But there's another even more important effect, that as these excitations scatter down, what they do is that they create lower energy excitations. So this is even more important because while this one was already not very efficient because of its short lifetime, and electrons here, not only they're more efficient, but they become very quickly much more numerous. No? So the energy scale that really matters is relatively close to the Fermi energy, but again, not too close because then the asymmetry between electrons and holes disappears. And okay, and that's basically just a summary. And so I'm running out of time, so let me just add few things. I mean, maybe these are rookie mistakes, but again, the idea was more of a tutorial. So what drives the directionality of the super diffusive spin transport? Okay, maybe naively, one could think that is the laser excitation and it's highly non-uniform. That's seldom true. So for thin samples, is relatively uniform. Now, of course, if you have two different materials, the laser excitation can be rather non-uniform, but usually it doesn't matter that much. And the reason is what I was showing you before, that while maybe in this layer we have several high energy electrons that are generated, and then maybe here we have fewer ones, but then as these guys travel away, they carry also their own energy, and now when they scatter, they can trigger secondary excitations and kind of make it a little bit even more uniform, the actual effective excitation of the material. And okay, but then, okay, what is it that drives the directionality of the super diffusive spin transport? Well, it's basically like what drives the standard diffusion. So usually you can have physical barriers for electrons, like the interface with the vacuum, but also differences in transport properties. Now, here I'm showing like concrete and mud as electrons in one material, they can have certain types of group velocities and scattering lifetimes, and in another material, they can have very different group velocities and scattering lifetimes. So this acts like, imagine like throwing very excited spheres here. Here they will diffuse well, but as soon as they get into the mud, they start accumulating in the mud. Anyway, so this is basically like just a diffusion process, and you can look at more details of the directionality here. And then how long do I have? Okay, I guess I can. 4 minutes. Oh, okay. So this is just, okay, then let me skip this. So this is just a reminder that, of course, when you have this kind of process, you don't just have spin transport, but you also have charge transport, and you need to consider different contribution from the different species. This becomes very interesting because whenever you have charge transport, you have also the formation of electric fields. And this becomes interesting when you have some semiconductors that are involved. But I think that Albert will present this. Now, let me just now show something new, okay? Something which is not a tutorial. So what we really worked on in this year. So now, to describe this, we want to calculate precisely the dynamics, the thermalization dynamics, and the transport dynamics of these laser excited carriers, and we do it with Boltzmann. Maybe I will go fast here. So you can basically couple the Boltzmann equation to, for example, the Maxwell equations. And now, what is it? So the Boltzmann equation, when you want to solve it numerically, has basically two parts. So one is the transport part, but now it's not super easy, but it's not even particularly complicated, so it can be solved. Now the really complicated part is the scattering part. So the scattering part is what I was telling you earlier. So it's a summation of all these possible transitions. So in practice, is a high-dimensional integral with all these unknown and time-dependent populations. Maybe I will skip this, what they mean. But what is important is that this high-dimensional integral also has inside Dirac deltas that enforce momentum and energy conservation. That scattering term was considered to be practically unsolvable numerically. And the reason is that because basically it's one of the reasons is that it's a quartic operator, so which means that it's equivalent numerically to a 5-dimensional tensor, which means that your numerical cost in principal scales has your precision to the power of 5, which is crazy. And also it's complicated to perform these high-dimensional integrals with Dirac deltas inside. And this is particularly important because, so this is a big topic in, for example, phonon transport. You want to enforce exactly momentum and energy conservation. And so basically, other available methods do not manage to do that. So usually what people do when handling the scattering term is to approximate it. So they try to reduce the order of the operator by approximating some of these populations. Now let's forget what these approximations are. And we don't want to do it, because if we do approximate, we cannot treat far from equilibrium distributions. But also one very important thing is the conservation of momentum and energy. So every single other, even approximated solver for, well, not even, all the other are approximated, they break either momentum or energy conservation. And this has a serious impact on describing thermalization dynamics. So we don't do this. And what we have done, so we have developed a new numerical method to solve the full Boltzmann equation with no closed equilibrium approximations. We don't fix populations, so we have any number of quasi-particle and bands. We can have complex dispersions, any number of scatterings, and then we can finally solve it, well, let's say for relatively simple systems, even on a laptop. And we have exact conservation of particle energy and momentum. And okay, I guess I can stop here, because I guess I'm already over time.
So how long would it take? You have less to slides? 2 minutes, yeah, we can.
Well, there are many more slides. Okay, maybe just very quickly, what is it that I'm going to show you? Or let's say, I'm not going to show you this. So we have also done some work on, we've also, just like 1 minute summary. We've also done some work on, so everything I showed you so far is the description of the transport, the diffusion. But now, what happens once you create a terahertz radiation? So once you create a terahertz radiation, now this terahertz radiation is created in, for example, the heavy metal layer. And how does it propagate through the sample? How does it get extracted from the sample? And so then what we have done is to basically have okay, this I will skip. So what we have done is to basically, okay, it's a bit too much. So, so basically modify the transfer matrix method to include a source, like a volume source, inside the sample. So then you can basically use this augmented transfer matrix method to really calculate precisely what is the terahertz emission that gets out of the sample. And also very interestingly, we can do the same. We can calculate how the terahertz radiation that is generated inside the sample is modulated by transport properties or dielectric properties in the sample. They change very fast during the excitation. So usually what people do is that they use a quasi-static approximation. So you suppose that your terahertz radiation is traveling through a material with slowly changing dielectric properties, but that cannot be applied in this case. So you need to describe the full time dependence of these changing dielectric properties, and they will add some frequencies to your terahertz signal. Okay, anyway, so I don't have time to show you this, and then let me just quickly go through the giant list of contributions that, of course, I've shown. One thing that I'm showing here is that measuring, okay, forget, I will not show it. Okay, I need to thank very, 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 very many people for their contributions.